when
This meeting is being recorded.
yeah, so that's a lecture. So if that's necessary, you need to reference to this meeting for the step by step of the operations. So then I can share you that with the recording. Okay, so the task of the today is to do this one. So you can see here, we have this that's a sample, which is usually what we do in the laboratory. Okay, so this is the sample which we do that in our Gemicas laboratory at the University of Tasmania. So this is that a non-stone of the rock sample, the diameter, which is 57.1. Then we have the H, which is almost that's 2.5 times of the diameter. Okay, you notice here, actually, so we were using a huge number of that the animals. So in this model, I have that 695,000 of the tetrahedral of the animals. According to the principle which we introduced before, we say for the FDEM, we insert the cohesive element between the faces of the tetrahedral of that the element. Yeah, so we know each of that the tetrahedral element that have 4 of the faces. So on each of the faces, so we were inserting a cohesive element. So that means so we can use that the number of the tetrahedral of the element multiple the 4. So then we have 2 adjacent of the tetrahedral element, so which will share of the one surface. So that means we can divide it by 2. Okay, so then roughly we have that 700,000 multiple 4. So then that's divided by 2. Okay, obviously, so we have that like that for the loading plate, it's unnecessary for you to insert the cohesive element there, since what we put in that in the failure, we were putting that in the rock sample failure. For the loading plate, so we wanted to consider that in the failure, obviously. So for the case, if you wanted to consider that's obviously for that unit access complex test in the laboratory. So in that case, the loading plate, which is much stronger than that for the rock, you wanted to consider that the damage or the failure. If necessary, so you can insert the cohesive element into the loading plate as well. And then the other things, so we have this the sample at the surface. So then external surface is unnecessary for you inserting the cohesive element there, since this is not contact with other of the tetrahedral of the element. Okay, so this is that's the task. Yeah, obviously here, to do this kind of modeling, we need a good of that in the GPU. Yeah, actually for do the 3-dimensional modeling, you need a good of that in GPU. So for all of the modeling which I introduced until this moment, I think that we have already gone through that in the 2-dimensional X complex test, 2-dimensional Brazilians test, and the 3-dimensional Brazilians test. So today we getting that in 3-dimensional unit X complex test. For all of the previous test, so I have already replicated that in Simpson's computer. Yeah, I just checked that in Simpson's computer in this morning. So I noticed that yeah, Simpson's computer have the GPU, which is GTX. I think that's is 3050. Okay, so the calculations, the compute capability, which is 6.1. I noticed that for the 2-dimensional modeling, like that in unit X complex test, Brazilian test. So evidence that of the GPU is not so powerful. So it's just taking a few of the hours to complete the calculation. Yeah, but I do notice that for the 3-dimensional or Brazilian test, Simpson's computer, which is taking about 48 of the hours. yeah, to complete that one. Yeah, I think that's for this one. If we have that the number of the element is that's so huge. Yeah, I'm interested to see whether that computer will be able to do this modeling. Yeah, for the Brazilian test, I think that we have that the number of the element, which is about 200,000. And so here, so we have that more than 3 times compared with that the BTX test. Yeah, I think that you will notice that most of the software, so with a number of the elements at this side, they won't be able to complete that in the personnel of the computer, mostly using the high performance of the computer. Like that, yeah, I'm sure our FPA, if you have a model which likens this, so which will have an element more than, I think we added this one, so which is more than 1.8 million of the element. Yeah, when did be able to complete that in personal computer? So you must using the high performance computer. But for our case, so if you have a powerful of the GPU, so this model like that in the computer, which I'm currently to using to making the presentation to complete this model. So I just need one latch about 8 hours. So then we'll be able to complete this calculation. So I have other more powerful of that in the GPU, so like an A100 to complete this one, just needed to have a few of the hours. Yeah, from here, so you can see when we do that in the engineer of the problem, so obviously what we did at this moment, we have this is all of this small scale of the laboratory sample. But we using that the number of the elements. So here that's about 1.8, 1.9 million. So that means if we use 1.9 million or around 2 million of the element, I think that we should be able to deal with that in the engineer for problem. At least that's for 2-dimension. Consider 2-dimensional modeling of the engineer problem. If we using that 1.8, 1.9 million of the element, we should be able to construct a huge of the engineer of the model. Okay, so before we do that, I firstly show you, so what is that in the modeling result should be looks like. So actually, which is this video. So I have shown you this video since before. So this is just a simple of a cylinder. Then we load in that. Then we see that the damage occur. Then the formation of the crack. Okay, if we given that 3 of the snapping shot, so which will looks like this at the different stages. So from that the damage to that damage accumulation, so then to formation of the macroscopic of the fraction. Yeah, obviously during that the modeling, so we can get the stress distribution, various kinds of the stress distribution as well. So that's similar to that in our RFPA code. Okay, so I said this is that actually which is compared with a sample which we did that in our Jamaican's laboratory. Yeah, so we can see here that's the stress strain curve at the initial part, which is consistent well, although that's later have this sign of the deviation. Okay, so for this model, obviously we can do that in the actual of the rock mechanics laboratory. We can put in that in the confinement around the sample as well to do the triaxial complex test. So then in that case, you can based on the triaxial complex test. So you are getting that under the different confinement. Then you can draw this kind of Moore circle. Then you can replicate it of the Moore cooling effect criteria. So what we use in that, actually, we use this as a kind of the calibration. So we do the triaxial complex test. So then we plot the results. So the results here should be, which is consistent with the Moore-Cooling fitting criteria. So then we can prove that's our software, so that is correct. At least we'll be able to put in that the tracks complex test. So as I introduced that before, yeah, so for the purpose of us to do this fundamental of the rock mechanics test is that to calibrate of the software. So if I have that in the software, when you be able to conduct the fundamental of the rock mechanics test, so then I'm not confident that it's that's to say I can apply that into the engineer problem. But if I have this can calibrate against the laboratory testing, so I can at least say, so I have that the base when I apply to the engineer of the problem. So you cannot say, so that's wrong. So at least my modeling, which will provide the insight to the engineer of the problem. Okay, so for this mode, we can do that more comprehensively. So like that, we have the granite. So you will have that in especially the coarse grain of the granite. You will have the grain that's there. So we can do that in the grain-based modeling. So we slightly modify this is the unique X complex test. So then implemented the grains there. So then we can do that in the grain-based modeling. I think here, so this is that's heart of the topic at this moment. So you will notice that a number of that's in the software, like that's in the PFC and the UDEC. So they do this kind of the grain-based modeling. But I can say, so we have that advantages if we compare with the PFC or that's in 3D. Okay, so for the 3D, we know that's in 3D, and so that's a distinguished element method. So for 3D, so in that case, each of that's in the grain, so they does not allow each of the grain fraction, or in other words, so if you use 3D to do the grain-based modeling, so you won't be able to get the transgranin or called that's an intragranin of that's in the crackers. So according to that in the previous study, then in that case, you will overestimate the elastic modulus and that's in the strength. Okay, so that's compared with the 3D, so we have that in the advantages. I think that we compared with the PFC, we have that in the advantage as well. So for the PFC, have the fundamental of the element, so that's Sophie. So PFC has the difficulty to represent the irregular shape of the grains. For the PFC to represent the irregular shapes, so then you have a few of the skin. So one of the skin, which is called the cluster, you put in that in a few of that the sphere glued together. So then in that case, you will be able to represent some kinds of the irregular shape. Yeah, you can see here for the grains, what we represented here, each of that's in the grain, which is have the arbitrary of that in the shape. Okay, so what are we using here, which is using that's called the velocity of the tessellation. So each of that's in the grain, so which is a velocity of that's in the element. Yeah, obviously, so for us to generate this grain, so as I said, so for our software, actually, we just do the calculation. We do not do the pre-processor and that's the post-processor. Although for the two-dimensional modeling, so we have a limit of the function to do the pre-processor and that's the post-processor. But for the three-dimensional, actually, we using that in the third party of that in software. Okay, so first here, for me to do this grain-based modeling, for the grains, I actually generated this grain using Laper. So Laper, I think that's the base of that in the software, which is prepare the grains. Okay, so Laper actually is an open source of the software that's free. So you can get in the source code You can download the source code from the website as well. You can modify that in the source code for your own of the purpose. So here, so we have that integrate neighbor into our software. So then we created this kind of grid, the grid. So after we created the grid, we using another of that third party of the software, Gmesh, or you using the commercial of the software, that's in the articles. So then to generate the meshes, then you import that into the model. So you can see, so even if that's for the Unix complex test, so they have already conducted many of that in the modeling using many of that software. But if you slightly, so add a little bit more of the difficulty, so like that's in the grain-based modeling, so then you will be able to publish a paper. So I just mentioned that I think that's in the last time I showed you one of that in my PhD student's paper currently is under review. So which is talking about the grain-based modeling. So what that paper actually do is quite simple. So you just introduce that in the grain-based modeling. Yeah, I shared the review comments to you as well. So you can see that the review comments actually say, so that paper, which is innovative, but that paper actually is only did that in the UX complex test. So just adding a layer of that in the difficulty. So that's the grain-based modeling. So then in that case, have good of that review comments. Yeah, obviously that paper is still in the second round of review. I cannot guarantee say that paper which will be accepted, but I'm quite optimistic that the paper will be accepted. Okay, so now let's do that. Okay, so here that's obviously that's we needed to use that not using the graphic using interface of the version. So we needed to use that we could that's in the high performance of that in the version. But actually, although we could that's the HPC, we can run this on the personal of the computers as well. It's not necessary. We mostly to run that in the high performance of the computer. Either of that's in the Windows platform or that's in the Linux of the platform. Okay, so here I will repeat that process. So you will notice that when I introduce, so at this moment, I'm introducing the first type of the test. So you can see when I introduce the Unix complex test, the 2D and the resilience 2D and 3D. So now I'm introducing UCS3D. So I have that in the modeling of the process actually is always that's the same. So you will see that's many things I'm repeating what I introduced that in my previous presentation. So hopefully, so through this repetition, you will be able to follow this process. Okay, so for all of that, the data, which I introduced until this moment, I have already shared that with you. That's all of that's available in Tintin's computer. Okay, I will show you that a little bit that's later. Okay, first to do the modeling, so that's the same. Firstly, we construct the geometric model. So then we build in that in the base of the model. Then we apply the boundary condition. Then we apply that in the material property. So then we give that in the control of the parameters. Okay, so for the previously, yes, I have already introduced that in the firstly of that in the step. So today, I will focus on to introduce that the material of the property for the three-dimensional modeling. Yeah, I think that's the last time when I introduced the two-dimensional Unix complex test, I introduced the material property for the two-dimensional modeling. Okay, for the three-dimensional modeling, actually is quite similar, but due to that the development process, so we have that in the format of the two-dimensional modeling and three-dimensional modeling is different. Yeah, actually perfectly, we should unify. So that's the format together. But this is reflecting the process actually for the two-dimensional modeling. So we have done so many of the development. So if we making that consistent with that. Yeah, so for us, for the development of our software, actually, we firstly focus on to developing that in the two-dimensional software. When we have the two-dimensional almost becomes mature, so then we starting to developing that in three-dimensional. And for when we developing that in the three-dimensional of the version, we are much more experienced and we have better idea about the data structure. So then the data structure actually is much more optimized compared with that for the two-dimensional modeling. Okay, so the first step, which is building the model, so either using the open source of the software or using the commercial of the software. Okay, so for my case, so here at my university, so we have the access to using ANSYS workbench, or that's in the Abacus. Yeah, and for myself, actually, I'm more familiar with Abacus. Yeah, then I building this model, so using that in the Abacus. Okay, so similar what I introduced before, I want to introduce how do you use the Abacus to do this to build in the geometry model, and that's the base of the model, since that's the commercial software. So you are supposed to do that yourself. Okay, for my case, what I given that to you is that I already prepare. So this is the geometry model, and that's the mesh model. So after that, after you prepared this model, so then you can let in the software. So that's the output. So you created a job. So then to write in the output of that in the data file. Okay, so then I directly to show you that in the output of that in the data file. The output of that in the data file, so which is here. So I will share you with this and that in the input file. Okay, so for Abacus, so that's very good. So after you generate your geometry model, you can output the meshes. So this mesh actually, which we're writing that into a text file. So that's a text file. You can open that and using any kind of that in the editor. Okay, so there is an editor. I usually use which is this one. So we know that in Windows have that Notepad. And here, that's called the Notepad++, which is this is an open source software as well. So that's free. You can download it from that the website. So this software, which is very good when you, which is edited the text of the software, the text of the file. So no matter how big of your file is, so you can see actually here I use a huge number of that in the element. So then that means I have this in the size of the, yeah, I have this that's 38 megabyte. So if you using that in the Windows Notepad, so it will take a long time for you to open this one. But if you're using that in the free and the open source of that in the software Notepad, then that's very convenient for you to edit it in this one. Okay, so I have already introduced this MP file a few of the times. Okay, so let's look at that in this structure of this the software. That's in the data file. Okay, for our case, so we have that in a rock sample. We put in that as a pot. So then we have the top plate and then bottom of the plate. Each of that's a separate parts. Okay, so then in here we define of the 3 parts. So each of the parts actually which is consist of the what is that's the nodes. Okay, you can see that's in the nodes, the first column. So that's the number of the nodes in the node. Then the second column, which is the x coordinate, y coordinate, that's the z coordinate. So it's easy for you to understand that. Okay, then after that, then the next one is that's the element. So element, which is the element connectivity. Okay, so we know that if I draw on a tetra of the hedron element. So we know that's the tetrahedron element which is like this. Okay, you have that's the 3 or 4 of the triangles here. Okay, suppose I have this, that you can see here, this is that the element, then the first one, which is the node element in the node, then that's the first of the node, then the second node, the third node, and then the fourth node. Okay, suppose I have this element, so which is I have that's the element number, so that's 1. So then that means I have that's 4 of the node. Okay, so I have that the node. Suppose I have that node. I have this first one. Okay, so here I use the different of the color. So then we have the first node. Okay, so that's this is the first node. Then that's the second node. Then the third of the node. So then the fourth of the node. Okay, then the node which is that in here, the first node which is the node RD. So which is 18 and 120. So that's this one. Then and so on. So then you will see here how many of that's in the element. Okay, this is for the rock sample. For the rock sample, we have using that in the element which is 658. Then 2003, 2030. Yeah, huge number of that element. Okay, so this is that's to represent the rock sample. Then below that, which is represented the top plate. So that's the same, which is still that's the node coordinate. So then the node connectivity. Okay, then that's the third of that's the plate. So which is the bottom plate. Then the data structure. So that's the same. So we have that's the node. Then so that's the element. Okay, so this is that's the information which we wanted to use. Okay, from here, we will copy this data. Okay, copying this data, I comment that into the compound representation. Okay, so we copy that the data. Like that in the first of the parts, so that's the rock sample. Okay, we have these 3 parts. And here, the first one, which we have that's the total number of that's the elements. So this one, we need to add in that the elements for the 3 parts, adding them together to give a total of the number. So that's we have that rock sample, which is 65,000, and then adding that for the plate. Okay, so then given that the total number of the element. Then the other one, which is given that the total number of that in the nodes. Okay, which is this one, adding that so on. Okay, so then we given that in the first part. So that's for the rock spaceman. Okay, so that's the data of the structure. That's the same. So we firstly, that's the total number of the elements inside of these parts. Okay, then here, that's the total number of the nodes inside of these parts. Okay, so that's the difference. For this one, which is the total number of the nodes of the 3 of the parts which we are using. For this one, which is just that's for this part. Okay, so then we have here that's the which I introduced that before, which is the first one, which is the X, Y, Z, the translation. Then this is the X, Y, Z, that's rotation. For our case, so we building the model in obstacles, which is satisfy our requirement. It's unnecessary for us to move in this plate. Okay, suppose I'm building a model. If I have this loading plate, which is far away, obviously, when you do that modeling, initially you won't have contact. It's very time consuming. In that model, you just moving this in the loading plate, and without it, that's the contact. Then in that case, so I have this, so for example, I have this is the y-axis. So this is x-axis, then that's the z-axis. Okay, I will directly to move this loading plate from this direction to this direction. So then I can here, I give minus, okay, suppose I have this distance here. So that's the 5 millimeter. So then I given that which is the minus 0.05. So then I will directly to move this, then the loading plate which will contact with that the specimen. Since for your modeling, there is no point for you to build just the movement of the loading plate. So that's time consuming and have no meaning. So what we want to do to building, which is that when we have the loading plate, which is loading that's in the rock sample, because that's in the failure. That's what we are interested. Okay, so then the remaining of this data structure, which is given that the element, which is just a copy the data from that the opcos that IMP of the file. Okay, element. Okay, then after that, which we copy that in the data for that in the top of the loading plate, and that's in the bottom of the loading plate. So you have this data structure, which is exactly that's the same. Okay, so that's the copy that kind of information. So then after that, we were given that in the initial of the condition. Okay, before I go that in there, I show you that in the file which I prepared that in here. Okay, we say based on that, we will prepare this one, the input file. So that's the element they note. Okay, so this is the input file is that what I just showed. Okay, so this is that's the total number of the elements, include all of the parts, total number of the nodes, include all of the parts. Then we have the 3 parts. Then the first parts, yeah, then the total number of the element of these parts and the total number of the nodes of these parts. Okay, so then here, this is just the copy. That's the element, the information, and that's the node of the information there. Okay, then that's the top loading plate, and that's the bottom of the loading plate, copying that information. Okay, starting from here, now we were given that the initial of the condition. We say for this initial of the condition, I prepare that's a preprocessor, so that's this one. Yeah, I have shown you this that's before. Okay, I have that. Yeah, so previously we have already constructed that for the 2-dimensional BTS, 2-dimensional UCS, 3-dimensional BTS. So today what I'm constructing, which is this one. So I will slightly modify this. So then I will use that to model the axis complex test. Okay, so let me open that one. So as I said, so this is that a very simple of the C++ program. Yeah, so you can use you need to have that understanding of the C++, or I noticed that so now many of the people which is using the Python. Yes, so Python, so that's a code which is usually, which is quite popular. So that's in machine learning. So you can use the Python to do that as well. Actually, I have that example, which is the Python, actually, which is included in this one. So if we read in that in the data from the opcos IMP file to that in the input file or a file, we can here prepare a simple of the Python script. The Python script will automatically to read in this file, then to transfer that into this file. If necessary, I can share you that in the Python of that in the code as well. Okay, so for this one, yeah, for all of the file which I introduced in that before, so I already put in that on the Tencent's computer. I can log in on that in Tencent's computer to show you where is that. Okay, is Tencent here? Can I log in onto your computer?
Yeah.
Yeah. Okay.
Yeah.
Great. Yeah. It's great since you are here. Yeah, I didn't notice that. Okay, so let's look on Tintin's computer to see. So where is that the information? Okay, I using that in the song login. Song login. Okay, it takes a while to start in the software. Okay, so let me wear my glasses. Yeah, so this is that's in Tintin's computer. Yeah, it takes a few seconds. Okay, on Tintin's computer, so I showed that this is that's in the border which we introduced since last time. So that's in the 3-dimensional of the predictions test. Okay, I show you where is that in the information which I saved in there. So I saved that so under the D disk. So D disk, then you have a folder which is called the HFDEM. Okay, you can see, so here, all of that. So what we, okay, so let me bring my tools to draw. Okay, so you can see, okay, so my tools, okay, my tools is covered by the, okay, I'm moving this away. Okay, so this tool is coming. So let me move in these tools so that I can see this tool. Okay, so you can see here. So all of that's in the file, which is I introduced in the before. So which is this is that we using that to prepare the initial condition, boundary condition, and that's in the material property. So that's available here. Okay, so the complete example we previously introduced in the BTS test, BTS2D, BTS3D, UCS3D. Okay, this is the complete example of that what I introduced during my presentation. I replicated that on Tintin's computer. And for you, yeah, so if you have that in your computer, which is the same as Tintin's computer, so then you can directly copy this one. Copying this one to your computer, then suppose if you wanted to do that in the 2-dimensional modeling, so then you just need to open that in the BTS. Okay, so open this one. Open this one, then you will have this two of the input file. Then you just need to copy this two input file to that in the same folder of the exe file. So then you will be able to get in that. Okay, so then you will be able to get in that in the completed of the examples here. And we have the GUI version. GUI version, yeah, so sorry, I still have not worked out that on Tintin's computer yet. I noticed that even if I use Visual Studio to build a program, any of the program, any of that in the GUI of the program which we need to be able to draw. I think that's related to the installation of the Visual Studio. Yeah, but I noticed that one of the students, I think that's one of the students could okay, I'm not sure. I think it's Tianzu. Yeah, Tianzu contacted me. So I noticed that he is able to install that in the GUI version on his computer, and he can successfully open that in the graphic using of that in the interface. Yeah, I think that's as long as we have that in the Visual Studio installed in that correctly, so then we will be able to run things on that. Okay, so for you to in this lecture, feel free to access since it's a computer, obviously you need to have that the agreement of the sensing to access her computer. Yeah, then to copy any of that in the software there. Okay, so let me close into to this one, come back into that's in my computer. Okay, so let me come back into my computer. Okay, we say here, let me clean my computer screen. Okay, I will using the, yeah, so each time I using this C++ script, I just slightly to modify this script. So then I will be able to produce this, the initial of the condition, this section. Okay, from that's the, from that's the velocity element property set, and then loading of the property set. Okay, so this section, where I will generate using this script. Okay, so before we do that, let's briefly go through that. I put that into the component presentations as well. Okay, in this component presentation, let's look at that in the structures here. Okay, so for our case, we have this and that, all of that is the load. Initially, actually, we regarded that in static. So you will notice that for the initial of the velocity, actually starting from the firstly of the nodes. Okay, this is the firstly of the nodes. So then that's in the loss of the nodes. You can see all of that in actually which is 0. So that means initially either I have the loading pledge or I have that in the rock sample. So they is static, didn't move in that. Okay, you may say we needed to move in that in the loading pledge at the top. So moving to the bottom, then the bottom moving to up. So that one is not through that initial of the velocity, which is through the boundary condition. Okay, I will introduce this, that's later. Okay, so then this is given that the initial of the velocity, then the next one, which is given that the element property. Obviously, so here, so we have the loading plate, we will regard that as the steel. And here we have that as the rock. So we needed to give that in the different property. How can I give that in different property? So I label that as this. So for the rock, so I label that as 0. So 0, which will correspond to a column of the material, which I will define that later. Then for the loading plate, I given that value is 1. Either if that's the top of the loading plate or the bottom loading plate, I given that the same. Since we have that in the material, all of that in the steel, either of the top loading plate or bottom loading plate, it does not matter. Okay, so this is that in the elemental property. Okay, you can see starting from the first element to the last of that in the element. Okay, so then the next one, which is given to the boundary of the property. So that's the boundary property, we given that into the node. So you can see for all of the nodes of the rock, so I given that since 0. So for the rock, actually, I do not need to give the boundary condition, or you can give that a safe weight. Yeah, but for that a small of the sample, a safe weight actually does not make a big of the difference. Okay, so then you have that in the top loading plate. Okay, here you notice that I separate the top loading plate. I given that a label that's 1. Then for the bottom of the loading plate, so I given a label of that since 2. So that's since I have that top loading plate, I needed to move that since down, and the bottom of the loading plate, I needed to move it up. So I have that different direction. I needed to define that differently so that I given that the different value. Okay, so then the next one, which is called the boundary loading flag. Okay, what does that mean? So this means, okay, we have the loading plate initially. You have the loading plate only have that contact at the top, and here you only have the contact at the bottom. So that means for your contact detection and then contact calculation, you only need to deal with the contact in here, or that's here. It's unnecessary. here, before you have any of the crack appears here, there is no point for you to deal with the contact here. That case, you will waste a lot of that the calculation the capacity. Okay, so this is the difference actually is our FDEM software compared with the other of that FDEM software. Okay, as I introduced before, at this moment around the world, many have 4 groups working on the FDEM. Okay, we are one of them. Then the other one, they publish both of the paper is in the University of Toronto. Okay, for they actually is no matter when you have it is the start of the beginning. So they needed to deal with the contact everywhere. Then in that case, they waste a lot of the computation capacity. So their software is much slow compared with our software. Okay, then the other one is I think that's the best one, yeah, in terms of the development. Although they didn't publish many of the paper, so that's the Los Alamos National Laboratory. So that's in USA. Yeah, for their case, they do not using the GPU to do the calculation. They're using the CPU. That's using the high performance of the computer, which is have a few hundreds or thousands of that CPU to do that calculation. Yeah, they actually did a lot of that development, although you do not see many of the publications from them. Then the other of that in the major group that's in the UK, so that's in the implicit college. So that's the original of the group. So that's Mojiza's group. We know FDEM, which is firstly developed by Mojiza, so as a PhD thesis. Okay, in China, we have that's 3 of the major group working on FDEM, but both of that, I think that's both of that involved in the application. Only have one of the group. So that's the development. So one group is that's in Wuhan University. Yeah, I think Liu Chunshen, I'm sure Guo Yang know him. Yeah, so his group, they just started to working on that around 2020, but they published a lot of paper about that. But for their case, they're mainly involved in the application instead of that in the development. Then the other one is that in China University of Geoscience. So I think that's Guo Yang maybe know him as well. It's called Yan Chenxing. So for his case, he is mainly working on that the coupling, which is the fluid coupling. So the thermal of that coupling. Yeah, and then the third one actually is that's Marcus former employer. So that's the Institute of Mechanics. So that's Li Sihai. So that one, they're coded, although they do not code that's in the FDEM, actually they coded that's the FD, they coded that's CDEM. Yeah, their code is the initial is originally from that the Swansea University, or that's in the original the place where Mojiza completed his PhD. Okay, that's a little bit far away. Okay, anyway, so that's if you initially needed to put the contact, you given a flag of 1, then otherwise, so you given a flag of that's 0. And here, that's given that's the 1 as well. Okay, so for this part, obviously, if you do that by hand, so it will be terrible for you to prepare this by hand. Yeah, so as I said, so what we do is that we use this script, which is prepare that's the data of the structure. Okay, so let's look and review this script again. I show you this script a few of the times. Okay, what is this script is that in here? Yeah, so most of that in comments are out. Comments are out, that means you do not need to use that. It actually does not function. So each time I slightly modify this software, this script, then generating the input file for the different of the purpose. Okay, so let's look at that in here. So firstly, yeah, so we have here is that whether you do the 2-dimensional modeling or 3-dimensional modeling. As I said, is the 2-dimensional modeling and 3-dimensional, we have the different data of the structure. Okay, the firstly, we do that in 3-dimensional modeling, we put in that 1. Okay, here, that's the total number of the element, then the total number of the node. So actually, which is from this of that's in the input file, which we prepare here. Okay, then after that, we need to give that in the label. Okay, for the, if we have that the element of rock are given that label, that's 0. So actually, I have that in the maximum number of the element, which is this one. So if smaller than this one, so that's represented the rock. If bigger than this one, which is represented the loading plate, okay, then for the loading plate, I put in that 1. Okay, here I need to stress that for the C code, you always have that index starting from 0. So that is why I do not put in the equal to here. Okay, so this is that, yeah, I'll generate the first, yeah, this column of that in the data. I using that single of that in centers. Okay, then the next one is that where I goes into here to prepare the loading property. So if that's in the node belongs to rock, okay, I given that in 0. If that's the load of the top plate, I given that 1. If the bottom loading plate, I given that 2. You can see you just use 1 of that in the centers. Then you will generate that in the information which you needed that in here. So that's the node property of that in the set. Okay, then the next one, which is called the boundary node of the flag. Okay, boundary node of the flag. So this one, which is I'm reading that and using this. Okay, so for here, you need to using that in obstacles assist you. Okay, so here, looking at that in here, I have that in, yeah, so the obstacles, okay, I need to reread that in the file. I firstly close into this one. Okay, I'm reading that in the input file of that in the, what we prepared here. Okay, so I have that in, okay, I goes into the file, which I save that in the file. Okay, user H7, OneDrive, then corporation. Yeah, so then, okay, so then let's read in this in the file. Okay, so here I define the sets. In Abacus, it's very easy for you to define that kind of sets. Okay, I already defined that in the sets. The sets, what I selected, you look at that, okay, I highlighted this one. I selected that, okay, so let me first remove the top plate. Okay, so let me first remove the top plate and that's in the bottom plate. Okay, so I have that set of the pots. Okay, so let me remove the top plate, removing that in the bottom plate. Okay, then in that case, we only have that in the rock samples there. Yeah, then we go into the set. So you can see what I selected that, which is the nodes at the bottom, and that's in the nodes at that's in the top. Actually, it's very easy for you to do that in the Abacus. So for example, yeah, I can demonstrate how you do that. Okay, we go into the assembly. So then you go into the tools, then that's set. Okay, so managing. Okay, if I wanted to select that's in the nodes at the top. Okay, so then I click on that and I say that's in the top rock node. I wanted to select that at the top. So you can do that and select into this. Okay, we have that Y-X. Okay, we firstly show that in the plane view. Okay, then you have this show that in the closing that in the perspective of view. Okay, then you can have that in the zoom up. So this part. Okay, so then you can select that. Okay, then you can see here. In Abacus, it's kind of very easy for you to see all of that and the nodes, or that's any of the element, any of the nodes which you wanted it to select in that, and so it's very convenient. So what I do is that, so I select, I create in that in the sections here. So here I have that in the, I created that in the 4 of the sets. Okay, firstly, that's in the nodes of the top of the plate, bottom plate, and then that's at the top of that's in the rock. So this is the place where I needed to use that for the initial of that contact, or is what I put in that in here. So you notice that in here, I have that in the boundary node. So if that's inside of that rock, I put in that in 0. If that's at the top or at the bottom, I given that in here, that's the 1, and here, that's the 1. How do you given that is that I use abacus to define this set. Okay, after this set is that's ready. So I actually use this to read into that 1. Okay, what I prepare that's which is here. Yeah, I'll copy that kind of information. Sorry, this is the output. So that's the input. Okay, I just copy that in the information there. You can see here, this is that's a list of that's the element, a list of the node at the top of the rock. And this is that's what how many of the number of the element is that, how many number of the nodes here. Okay, then the next one is that at the bottom. Then that's the number. So here, it's very easy for you to calculate this number since of course the data, which is quite structured. So as I introduced before, so each line you have that 16 of that number. Then you only need to calculate that how many of the line. Okay, so let's look at that in one example. We have here starting from the line 100, and then the lost line I have that 196. So if I wanted to calculate that how many of that's the note here. So what I do, I can simply using that in the calculator to calculate it. Okay, I have that in 196. So minus 100. Okay, so since here I have that start line and the bottom line, so then I needed to plus 1. Okay, so this is that total number of the line. So then I multiple 16. So then that's the total of that the number. But I have the lost line actually missing a few of the number. Okay, I missed the so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so then I have that's minus 9. Yeah, then that's what is the number here. So 153 for 3. Okay, so then what we do, that's the rebating. So I read into that 1. You can see when I read in that, I give it a flag, given that 1, and then the bottom one, I give that flag 1. Okay, then for the loading plate, I give the flag 1 as well. But here you need to be careful. For the loading plate, in opcos, so loading each of the parts, you have that numbers separately. But for our code, we have that number which is continuously. So then for the top plate, regarding that as the second of the parts, you need to add in this one. And for the bottom plate, you regarding that as a third of that part. You need to add in that in the total number of the element, total number of the nodes, the first parts, the second parts. So then you were given that in this flag. Okay, then after that, you run this program. So run this program, you can debug into this one. So like in this, yeah, I can check in that and whether that's reading correctly. You can see, you can put your mouse there. So which will show you what is the current number we should read. So what is the current number you read? Okay, so then you run this this one. Okay, so then that will generate this part. Okay, so here which will have that's the output. So output which is here. Okay, which will give you that's the information of that's the velocity. So then the information of that's the element property, and that's the loading of the property, bounding property. Okay, then you copy of them, copying this one. So then you place that for this part. Okay, which is this part. So the notes, the velocity, element property set, loading property set, boundary load property set. So then that you given that the information. Okay, so then the remaining here, so that's the property. Okay, you notice that in here we have that 0. Okay, each of that actually which is represented the material property. We have that, okay, we say rock is 0, so plate is 1. Okay, then that means the first column, what we given that, which is the material property for the rock. Then the second column, which is given that's the material property for that's the steel. Okay, so here I put in that into the compounded presentation. Let's come back into the compounded presentation. Okay, what is that the property which we want? Okay, this is that the property. Looking at the data structure, so we firstly have that the material property. We have the first column which is represented for the rock, then the second column which is the material property of the steel. Okay, I will explain each of that the meaning of that material property later. Okay, firstly, let's go on. Then the next one, which is we given the boundary condition. The boundary condition, we say we define that in the value, so which is here. Okay, we define 0. So the first column 0, so that's the rock. Then the second column, so that's 1 is the top loading plate. Then the third column, which is the bottom of the loading plate. You can see actually both of that it's unnecessary for us to deal anything. Only things what we put in that here. We have the top loading plate. So we given that moving downward, the loading plate moving downward. So that's we given elective value, which means we have that's the y direction, which is pointing upward. So we have that's the opposite y direction. That's why that's given elective. Okay, then the bottom loading plate, we let moving that up. So we moving that, we given that here 0.05. Okay, then we can, through here, we can control whether this given that velocity, given the force, or given that the quarter of the boundary. Okay, if we have that 0, that means we add nothing. So like that in rock, we making that completely free. We didn't give that anything. Okay, the top loading plate. Okay, we given that 3. 3 means you add a velocity. Okay, we have that velocity, which is 0.05 meters per second. Then the bottom loading plate, we given that velocity is 0.05 meters per second as well. Okay, so this is that's given the boundary condition. Okay, then the next one, which is given that's we say between of the tetrahedral of element, we were inserting of the cohesive element. Okay, we only need the insertion of the cohesive element into the rock unless to the plate. So that means we only need to have one group of the data that's sufficient. Okay, so here I will introduce that later. Okay, then this part, this is the control how we insert of the joints. Okay, here later I will introduce the grain-based modeling. So that one I will introduce this in detail. Okay, at this moment, let's ignore this one. I will focus on to introduce the material property, and that's the joint of the property. So this is what we essential to the modeling. Okay, let's go into first the material property. So we have the material property, the first one, which is on damping. So as we said before, we have this is that the explicit code. Explicit code actually is based on that the Newton's second law. So Even if we have this problem, the unit X compressive test, actually we regard that as a static problem. But actually, we more than the static problem, we treating that as a dynamic problem. Okay, for the dynamic problem, then you need to put in that in the damping to make that becomes static, or that's the quasi-static problem. So then we needed to give that a critical damping, or call it that's viscous damping. Okay, for this parameter, how do you calculate that? You are based on this formula. Okay, H, so that's the length of the element. M, okay, so M here at this moment, I say that's M which is equal to 1. Then rho, so that's the density. Then E, that's the elastic modulus. So based on this, you will be able to calculate this parameter. Okay, so that's the first of that's the material property of the parameter. Then let's look at that in the second property. The second property, so that's lambda and U, so that's lambda constants. Okay, lambda constants, as long as you know the elastic modulus Poisson's ratio, so then you can calculate the lambda and the U here. Okay, so these two parameters, which is calculated based on this formula. Then the next one, which is called a homogeneous index. Okay, so here, this is follow what is in our RFPA. So that's the Weber distribution. So that's actually is M in RFPA. So M, if we have M, which is a big value, that means that's homogeneous. Otherwise, M is a small value, we can get the heterogeneity. Okay, we skipping that one since that's completely the same as that in the RFPA. Then the next one, which is given that the contact penalty. Okay, when two objects which contact each other, we wanted to prevent that's the penetration. Then we need to define a contact penalty. So according to our experience is that we using 10 times of the elastic modulus. Okay, then the next one, which is considered that contact damping. Okay, when you have the different object in the contact, which is where the damping is different, we say, given that the example. Okay, so let's go to the next one. We making that simple of that in the case is that if we draw, like we play a basketball, when you drop in the basketball, which will have very few of that in the damping, when you drop that, almost will bounce that into origin of the head. Yeah, but if you bump it, like that in a sand back to the ground, when you drop into that, it's won't move, it comes back. Okay, so that means during that contacting, which is causing the damping, obviously the damping which is related to the material property. Okay, we simplified that we using two parameters, so which is that's in the parameter B and T, which is both in that's in the damping. Okay, you can see here, this figure, back control, this B and T, so we can represent the different damping. Yeah, for example, if I let him B equal to 1 and T equal to maximum, so this is actually what I put in that in the here. That means we do not consider any of the damping. So when I have the initial of the energy is there, then I drop in that, which come back into this energy. Okay, if I wanted to implement that in the damping, then I can only just that in the B and T this parameter. So you can see here, I have initial of the energy is here. Then after that, so you have that energy that's here. So that's the representative value cancer of the damping. Okay, this is that and this, what is the meaning of this parameter? Then the other one is that in the friction. Okay, after you have the failure, which is full, then you will still have that in the friction, where we call it that's the residual of the friction. So actually, it's the parameter which is here, so which is tangent of that in the residual. Okay, so let's come back into here. So this parameter, so which is tangent of that in the residual of that friction parameter. Okay, then the next one you notice here, element density. I use that very big of that the density. I instead of, okay, this is that the non-stone. Non-stone actual of that is the density actually, which is 180 kilograms per cubic meter. So this is that's the actual value. So the value which I using here, actually I multiply the 5. So this is a kind of that's the mass scaling. Okay, the mass scaling, why I need to use that mass scaling? So you look into that, we have that in the explicit fundament, you need to have a time step. Time step must be small enough. If you have that in time step which is too big, the calculation is not stable. But that time step actually which is related to the density. Okay, if you have that the density is bigger, you can use a higher of that the density, then you can increase the time step. That's what I use that to do. Okay, this is that the mass scaling of the concept, which is frequently. If you have the experience to use AS-Dana using that the concept of the mass scaling as well. Okay, I will come back into the influence of this that's later. Okay, so this is that. Okay, then the next one, which is the homogeneous index. So that's the same as that's aim of the concept. That's in RFPA. Then the last one, so this is that's the different type of the element which we define. For this tetrahedral of element, we use that in 21 to represent the tetrahedral of the element. Okay, so this is that's the material property. Okay, then the next one, what we wanted to is to give that the joint of property. So this I introduced a little bit of that last time, which is the same as that previous one. Okay, so firstly, let's look at this. The first three of that the parameter. Okay, we say we using that the Berkeley of the strength criteria to check if that's the cohesive element which will fail or not. Okay, the cohesive, if you're using the Berkeley criteria, you need to specify. So what is that the, okay, let me change it, that's in the color. So what is that in the cohesion? Homogeneous index, so that's the same as that's in RFPA. Okay, so then that's the tangent of that in the friction's angle. Okay, so then that's the tension of the strength. So that's sigma t, C and sigma t. So this is that what is that in the Berkeley Philip criteria. So it's easy for you to understand that. Okay, after that, so we have that in the parameter which is called the flux energy. The flux energy, so here, as I said before, actually here, we do not have a good of the best to determine this two parameter, especially for that the model 2 of that the fluctuating energy. Okay, for the model 1, there is an empirical formula. So we use this empirical formula. Then for the model 2, actually we just multiple 10. Most of the cases we multiple 10, or we multiple between 5 to 10s. Yeah, here we do not have that in the reason. And then the other one is that you need to put a penalty. So we say between of the tetrahedral element, we insert of the cohesive element there for to burden the failure. But before the failure, so you actually that's the continuous. Okay, so you mostly given the reasonable of the penalty, making sure initially you insert the cohesive element that won't affect the continuous behavior. Otherwise, if you have the material property given not appropriate, so then you have the insert of the cohesive element there, which will influence the continued behavior. So our experience is that we given that in which 100 times of that's the E. So when did they have a bigger of that's the influence? Okay, so that's the cohesive element which we insert there. Okay, so this parameter which is defined by ourselves, we just for the 3-dimensional. For the 3-dimensional, we insert the cohesive element actually have that a 6 of that nodes. So 6 of the nodes since each of that is the triangle, and 2 triangle putting that together. Each of triangle have 3 of the nodes, then 6, so that's 2 triangle, so that's 6 of that node. We define this type of the element we use in 23 to represent that. Okay, so that's what is that meaning. Okay, so then with that one, So then we prepare that's the input file. Okay, so this is input file, so which is this one. Okay, so the input file, which is prepared, that's at this one. Okay, so this is what I introduced, that's the procedure to introduce how we generate this. Okay, then after we have this, then we copy this file and with a running control of the file. Okay, running control file, I have not introduced that till this moment. So here, actually, which is control, how do you do that in the modeling? So here, yeah, like that control to do the two-dimensional modeling, and that you control the varies of that, whether do that the excavation, whether you will consider that sub-coupling, hydrocoupling, or the fluid structure interaction, where you implement the discrete inflection network model, where you do that in the grain-based modeling, yeah, well, do that in the strength reductions, that method. Okay, here I will introduce that later. Okay, then here we construct that in the input file, then you just need to copy. So this is input file. So then you put in that into the exe file. Okay, we have that in the exe file, which is here. Put in that exe file, then you run that, then you will get in the results, and so that's here. Okay, so let's look at that in the results. Okay, so the results, yeah, this shows that during the calculation. So firstly, you have that's the macro damage. So then after that, that's the formation of that the failure. And here, that's the crack. Okay, so here, which show macro damage, and that's the real of the damage. For your case, you only need to show that's the macroscopic of the damage. The real of the crack, you can justly, yeah, filter that and only show that's in the crack instance there. And here, then you can get in that in the stress strain curve like this. Okay, so during the calculation, I introduced that I using that in the mass scaling. Okay, obviously this mass scaling, which will have the influence of the results. Okay, then I did the parametric analysis here. Okay, firstly, I introduced why I needed to use the mass scaling. Okay, if you have the experience to using the LS data, you will notice that LS data using mass scaling as well. So the reason I using the mass scaling, which is related to this critical of the time step. Okay, for discrete element or FDEM or any of that using the expression method. So you have that the stable of the time can be roughly calculated using this formula. Okay, this formula you can see here, HMIN, so that's the length of the element. So lambda and U, that's the Lambda constant. Then rho, so that's the density. You can see if I increase that's the density, then I keep in order of the parameter does not change. That means I can increase of the time step. So if I have an increase of the time step, that means I have the calculation in the length of the time. Okay, then what I do is that I multiply on M. Okay, I make that I have that M, which is between 1 and I calculated here for the different value. 1 till that's 1,000. Okay, you can see when I have that M equal to 5 equal to 10, M equal to 100. So you can see to get in the stress strain curve, almost it does not have any of the influence. Obviously for the post-failure stage, which have some of the influences there. But for the before that post-failure, actually does not have big of the influence. Yeah, this mass scaling may influence the failure patterns as well. Okay, I show this and that. And yeah, if M equal to 1, that means I didn't use any of the mass scaling. Okay, here I use the 5 mass scaling. If you compare these two of a figure, actually you almost didn't notice any of the difference. That means I apply a small of the mass scaling wouldn't influence my results significantly. Obviously, so when we put in that a big of the mass scaling, which have a bigger influence, you can see here, even for the stress strain curve, notice that some of the oscillations is there. Yeah, so that's the effect of the mass scaling. So this is a little bit tricky. You can use the mass scaling a little bit to increase time step, then reducing the calculations time, but that will have the influence. And then the other one is that you notice that for our modeling, we have the loading rate. We're using the loading rate, which is 0.05 meters per second. So this is a very big of that in the loading rate compared with the laboratory test you do that in the laboratory. I think that in the laboratory, the standard of the International Society of the Rock Mechanics, which is say every second you just play 1 megapascal. So that's in the laboratory, you have the loading rate, which is much smaller than this one. Here, we using that 0.05. Then we did that analysis for the different loading rate. You can see the loading rate do have an influence either of that BTS test or union axis complex test. But I noticed that for the union axis complex test, then what we do that here. So if we have the loading rate even that's below 0.2, so you have here does not have a bigger of that influence, or they have some of the influence in the post failure of that zone. Okay, so that is for you to do the modeling, you need to choose a proper rate of that the loading rate. If you have the loading rate too big, like in this one, we apply that the 1 meter per second, then you have that no longer you have that the static or quasi-static problem. Actually, what you becomes that which is a dynamic of the problem. Yeah, okay, so after you calculation, then you can use that in the parallel view, which is I show that in the parallel view, the result which I put in that in my presentation actually, which is from that's in parallel view. Okay, parallel view, that's an open source of the software. Yeah, I will not introduce that. So I will focus on introducing the part, so which is related to our software. Okay, so I will stop in here today. Okay, so that's 4 minutes early than that's the scheduled time. Okay, so I stop in here. I handed that back to you. Yeah, Guoyang.
Okay, thank you, Professor Liu, for your excellent report. Now, we may have questions for Professor Liu. Is there anything we needed to talk about? Any questions from teachers and students? Any questions?
Yeah, I think it's difficult for the students to ask questions, so we may ask teachers to ask the questions.
Hello.
Hello, Mark.
Good morning.
You are there.
Okay.
Yeah. I was thinking you are busy. Yeah, so was not here.
No, I just another meeting. So Guoyang has to give me the license. So I just interrupt another meeting and I jumped this meeting. I listened very carefully and very good presentation. Thank you for patience, Professor Liu. Okay. And I have a question about the preposition. I noticed that the effect of mass scaling, the 21 page, your presentation, 21 page. Can you tell me how to calculate the M value? Because our RPA has the M value, 21.
Yeah.
The last 21. Okay.
Yeah.
Okay.
Yes.
This page. RPA has a lot of the M value, and the other the EDM has a M value. Can you tell me how to calculate the correct M value from the laboratory? And when I have get the right or correct value of M, so I can put into the numerical simulation, and then we calculate the practical value for us. So how to you can say the M is equal 1 or equal 5 or equal 10 equal 100 equal 1000. but blah, blah, blah. Why M is 1.5, 2.5, or 3.5? How to calculate the M? How to get it, the correct value, M? Okay.
Yeah, great. Yeah, good question. Yeah, okay, firstly, so the M value here actually is different from that's the RFPA. So M value, which is the same as that for RFPA, so actually is this one. So we have this value, which is exactly the same as that's the value of that's in RFPA. We have this one. So here, this is that's the M, which is represented the heterogeneity. I think that's in M in RFPA, so which is represented that heterogeneity. Yeah, okay, I firstly answer this question, then after that I explain what is the M, which we use in that in the mass scaling here. Okay, so here, which is that as we said, this value is the same as that in RFPA. RFPA, so we implemented the heterogeneity. Okay, so what we have that's we have this that's a probability. Okay, suppose we have this that's a parameter like that's the strength or that's the elapsed border. We say if we give that different M, okay, if we get the M which is equal to 1.1, so then you will have that's the value which looks like this. Okay, if we have that's the M equal to 5, so which will looks like this. Okay, if we have M which is equal to 100, so then you will have that's the single of that's the value. Okay, here we use that the same of that's the concept for this one, which is we call it that's actually which is exactly follow that in RFPA. We call it that's a homogeneous index M here. Yeah, actually, so we have another of the parameter which is control here, whether we use this parameter or not. For this FDEM modeling unit X complex test, actually we didn't consider any of the heterogeneity, didn't use that M. Okay, suppose if we wanted to use this M, and for this value, how we determine of this value, like that based on the your macroscopic observation, or that's the field observation. So here, actually, I spent a major of the effort to working on this topic. But that's about, I think that's now is about 20 years ago, or that's 15 years ago. Is still at the time when I was working as a PhD student in Sweden. I really spent the effort to how to determine this method. I think this slide, which is starting, I think that's starting from a professor in Hong Kong Political University, which is Professor Wang, which is he initially proposed this question, then starting to working on that. Yeah, she did some of that study, but didn't complete that. I actually follow what her study, then I made the detail of the study here. Okay, I can share you that's one of that's in the paper. I actually, so on this topic, I published a comprehensive of that in the paper about this topic. Okay, so let me find that in the paper. Yeah, so I needed to remember what is that the name of that in the paper. Okay, so let me search that in the my page at the University of Tasmania. So then let me find that what is that in the paper. Okay, the publication. Yeah, I think that's a paper. Yes, it was published some time ago. Okay, so that's 2001, 2020. Yeah, I think that's around 2012. I published that paper. 2000, yeah, so should be somewhere around here. Yeah, it's this one. Okay, so let's look in reading this paper. Yeah, so here I actually spent the major effort to introduce that and how we, yeah, although this paper was published in 2012 after I moved to University of Tasmania, actually the work was completely that when I was a PhD student, so I didn't publish that at that time. Okay, so here we actually compared two of the methods. One of that is grain-based method, and the other one, which is using our FPA, that's the M value. Okay, so what we do is that we firstly do macroscopic of that the observation. So then after that macroscopic observation, we extract, so that's the information. Okay, so you can see here, I do comparison. One of that, I do that in the grain-based modeling. I do not, I explicitly to consider the heterogeneity. Then the other one, which I do that, which is I use that in our Weber distribution. So I do not explicitly to consider heterogeneity. I use that the M to consider that the Weber distribution to consider that the heterogeneity. Then I compare these two cases. Okay, so after the comparison, then I get that a method to determine of that the M of that value. Okay, what are we starting from that Weber distribution? Then we do the transformation. Then for the macroscopic observation, so we get that in the macroscopic, that's in the cracking of the lens. Okay, so for that in the cracking lens, we represented that to that statistic of the relationship. Okay, then after that, I get in this formula. I think this formula actually is initially getting that in, by Professor Wang in Hong Kong Political of that university. Yeah, so I have that since, yes, is this one. Yeah, so I started that in his paper. Okay, so then we get in that in here. This is through that macroscopic observation. So the crack in the lens, so then the number of the crack. So then I fit in that. So using a power of that in the relationship. Okay, when I have that in the power relationship, I have these three type of the rock, which is that's in Sweden, three type of that's in rock. Okay, based on that, we at the same time we do that in the mechanical analysis as well to get in the uniaxial complex with strengths, elastic modulus, yeah, and that. So then we from here we determine that's in the M of that's in the parameter. Okay, so then based on that, I determine yes, M. I have this and that. This that's in the formula, and for Z, I determine that based on the macroscopic of that in the observation. Okay, then I get that for the average of this, and I have M equal to 253, and the lap, yeah, so and so on. So then I use that to do that modeling. Then I compare these results from the grain-based modeling and the results in the Weber distribution. We call that the macro mechanical of that in the modeling. Okay, so from here, so I can get that to determine based on the macroscopic observation to determine that the M parameter. Okay, so this is that's the M of the parameter. So which we use that in here, that's the same of the concept with that in the RFPA. Okay, then the other one, so what we using that in the mass scaling, so this parameter, so actually, so here, this is differently from that's in the M there. Okay, what is that you notice here, I using, when I given that in the input parameter, I have that in the density, so I put in that in 9,003 kilogram per cubic meter. But actually, so the rock which we put in here, this is limestone. Limestone, we measured that, so which is 1,800 kilograms per cubic meter. So then here, I using this one to multiple M. So this is that's the M, that's for the mass scaling. So if I have making that M, which is equal to 5, so that's exactly which is represented here, 900. And for the steel, so we have that in the density, which is 78, then I multiple 5. So then that's what I get in this value is here. Okay, the purpose I do this mass scaling is that I wanted to increasing the stable of the time. Okay, for the stable of the time, for the expression finite method, you have the stable of the time step, which is this one. Okay, suppose if you have the base and you have the material property, so that's the same. Only of that, if you wanted to increase this one, you notice that this divide is the multiple. Divide, that's I need to increase that's the density. So then that's the why I multiple on M, so multiple the density. Yeah, obviously here have some of the influence, but we notice that actually we can say here, actually even we put in that in multiple 10, yeah, you won't get how bigger of that the influence either in terms of the stress strain curve or in terms of that the failure pattern. Okay, yeah, so did I answer your questions, Professor Buck?
Okay, apparently very well. Okay, so in RPA's M's value, I read lots of the reference of the data. I have got it that the M value come from the laboratory, so he can made a lot of the models and observe the models damage or correct. So if he can make M, for example, M equal to 1, and he observed the model's damage. If he found that, oh, M equal 1 is correct, is very similar with the the laboratory model, and very similar with the numerical simulation result. Okay, M is 1.
Yeah,
Okay.
I think that using that method, you need to do a huge number of the laboratory tests.
Okay.
Yeah, I think that one. Yeah, actually, I'm working on that one as well. I initially, when at the beginning, when I started to work in my PhD, so I published another of that in the paper. I think that's at that one, I used the method which you introduced, so that's there.
Okay.
Yeah, so for this one, I think that's in the engineer geology. So this paper, yeah, so do I have that in the full of the access? Okay, I do not have the full access. So let me log in on another of my computer. Yeah, I can show you. So that one through do a number of that in the laboratory test to get in the aim of the value. Okay, so bear with me for one moment. Yeah, so yeah, I think that's one. Yeah, so this is that's more widely used in that's in the method to determine of that's the aim. So they're actually using the least square of the method. Okay, so okay, so let me see where is that one. Yeah, so I think that's using this one. Firstly, we do many of the laboratory tests. Okay, then we get an assembly of the strengths of the laboratory test of that the results. Then we based on that laboratory results to get the statistical distribution. Okay, then after that, we do that the least square of the method. And then in that case, you will get that in the parameter A. So that parameter A, so that's actually what is represented M. Yeah, obviously, so here that's the different researchers using the different method to determine the M. So here, that's the Weber distribution, which is widely used to represent the statistic of the materials. Actually, it's not only that for the rock initially, so that's using that for the ceramics. So the order of that the materials as well. Yeah, you're right. Yeah, so that's yeah, so the order of that method to get determine that in the M value.
Okay. Any questions?
Hello, Professor Liu.
Yes.
I'd like to ask how the input parameters should be adjusted if there are problems in the modeling process. I think the parameter may have many values. We can get these values from the empirical formula. How we can use the right one to use in the modeling process?
Yeah, that's a good question. Actually, this is a big problem for all of that in the numerical modeling. Yeah, so the numerical modeling is always have that in the problem. How do you correctly to choose the parameter? Especially for this kind of modeling, which is considered that the from that's the macro behavior to tier that's the bigger of that scale. Like that to choose the parameter, for example, for that the PFC, for you to use the PFC to do any of that modeling, you need to firstly have a calibration of the input parameter, since we know what we get in that from the laboratory parameter, which is represented a macro scale of that, and the parameter, what you get in that, which is the real physical mechanical parameter of the rock. But for the numerical modeling, like in the PFC, what you have the input parameter. So actually, that's the another MRCRO, because that's still called the macro, but that's the small scale of the parameter. Then in that case, for PFC, for you to do the modeling, so you need to firstly do the typical of that, the union axis complex test, the resilience test, and the tri-axis complex test. So then you mimic that's the laboratory scale of the sample. So then you determine your macroscopic parameter. So then that means your input parameter with that's the parameter which you get in the laboratory, which is completely different. Yeah, so this is all pleasant to the cases. Yeah, so for the our software as well. Yeah, so but I think that's for HFDEM, the parameter is not so complicated compared with that's the PFC, or that's the discrete element method. Yeah, I think that's what I introduced in that for our software. So we have that in the parameter. Many of the cases we can use that in the laboratory of that in the testing results. So like that, yeah, so for example, when we determine that's in the lambda and U, yeah, so you can get in that from the laboratory test, you can get in the elastic burden, and that's in the person's ratio. So then we can use in the elastic parameters to get in the lemma of the constants. And then for the contact penalty here, yeah, so if you read that paper, there is have a wide of that range from 1E that's to that's the 10E. According to our experience, that we put in that in the penalty, so which is 10 times the E, so that does not have a bigger influence. Then for the strength of the parameter, so for the working, like that in the cohesion, the friction angle, and that's in the tension strength. And here, this parameter, we can directly to using the parameter which is from the laboratory test to get in the cohesion, the friction angle as well. But we do have this that's in the parameter like in that in the fracture energy. So this kind of a parameter actually is really that's difficult instance to choose, and this it's difficult for you to measure that's the fraction, the energy that's in the laboratory as well. Yeah, we are thinking this is the fracture energy, which is related to the macroseismic monitoring. Macroseismic release the energy. Actually, so we are spend the effort here to relate it to this, we cleanse that and we will be able to model that macroseismicity as well, which is similar like that in our RFPA. So our RFPA, we put in that in the acoustic emission. Okay, so for our RFPA, we have that in the constitutive, that's in the equation, which is like this. Suppose we have that sigma, then we have that in the epsilon. So we have that in the linear elastic, then here, okay, depends on if you have the tensor failure or that's in the shear failure. Okay, suppose if you have that's in the tensor failure, so then you have that's in the residual of the strength. Okay, then after that you give that into 0. Okay, then you have this energy, so that's released in RFPA. We call that in the acoustic emission. So then we related it to this energy related to the macroseismicity, which you monitor that using the macroseismicity monitoring system. And for our case, we have this that's a little bit that's more of that complicated. So we have this initially elastic. After that, we have the elastic plastic. So then we have that. Okay, we have this part of that, which is that the energy of that release, so which is related to this parameter. Okay, to answer your question, I think that yeah, so this is a difficult question for all of the numerical simulation. I think that I cannot 100% answer your question, but I think that we have that the most of that in the parameter, which is in this software. So we have that can use based on the laboratory testing of the results. We chosen this parameter, although we still have that a few of that in the parameter, like that in the fluctuate energy, like that in the penalty, the contact penalty, and the fluctuate of the penalty here. It's difficult to determine. We need to base on the experience.
Okay, thank you, Professor Liu.
Thank you, Professor Liu.
Yeah, you're welcome.
About 2 hours past. Any questions? 其他同学还有问题吗？马老师还有问题吗？现在时间也挺长了。
Yeah,
如果有问题，我们再有问题。
Yeah, Professor Bao probably have other of the activities there.
马老师可能这个，马老师看不见你啊。
吗？
Yeah, guys, he has other meeting. He is in the meeting.
Professor Liu, I have the last question. The title of this report is the simulation using the GPGPU-parallelized HFDEM. Have you calculated some engineering examples at present using your code?
Yeah, that's a good question. Yeah, so obviously, so we have this that in the software, which is self-developed software, for you to convince the others to say, so your software, which is suitable to start in the engineer of the problem, we firstly need to do a number of that in the calibration. Yeah, I think that's is what we are doing that's at this moment. Yeah, but obviously we are also collaborating with other parties like that in Australia. So we collaborate in that with CSO and Monash University, Melbourne University. We do that in the engineer applications as well. Yeah, but till this moment, it's the application which we did that, which is quite limited. Okay, I can give you a few of the examples which we use in this to solve that in the engineer of the problem. Okay, I starting that from firstly, which is from publications of that in the example. Okay, the first example which we use in that to start in an engineering problem is that completed by one of my PhD students. So we collaborated in that with CSO. We started a tunnel Yeah, tunnel actually, so that's our purpose in that, and so this tunnel, which is are quite familiar with in that. Okay, so let's look at that in one of our published paper. So we started in that one. So one of my PhD students studying a deep of the tunneling. Okay, so which is this one? Okay, this is considered as a tunneling which is constructed using the drill and the blasting method. Okay, so this tunnel, which is a Swedish of that tunnel, which is a developable using that for the nuclear waste disposal. And this tunnel, which is buried deep in the underground. Okay, so then that's the in situ of the structure. Okay, so that's the details of that the tunnel. Okay, yeah, that's the constructions of the procedure. Okay, this tunnel, okay, is excavated using the drill and the blasting of the method. So the last one, which is using the smooth of the blasting. So you can see for the smooth blasting, the quality of the smooth blasting, you need to make sure you have still, after the blasting, you still have half of the borehole, which is appears there. You can see here, they did that quite well. You can see from the tunnel surface, the last step of this last smooth blasting. For the both of the places, you can still see half of that in the borehole, which is still that's in there. Okay, the purpose of that one, this is actually when I was working as a PhD student in Sweden, I worked on this project. At that time, I used that in the RFPA, did that. Since RFPA, at that time, we RFPA do not have that in the dynamic of that version. Yeah, what we started in that, actually, which we consider that as a static problem. Yeah, obviously, so it's question when you building that rock blasting using a static of that in the software. Yeah, so myself is not satisfied with that one as well. That's why when I supervise, so this is actually a Chinese of the PhD students. So got Han, Dr. Han. He has already graduated, so he's now working as a associate professor in Chinese university. Yeah, then I also him to redo that one. Okay, so redo that one, obviously, so this is very complicated. We wanted to be able to model that in the flow of the process. So we ignore all of that in the middle of that in the process. We only model that in the last step, which is the smoothing of the blasting. Okay, so here that's in the modeling, which he constructed to model that in the smoothing of the blasting. Okay, we divided that into that's 4 of the zone. Okay, we firstly put in that in the borehole here. We initially added that in the borehole at the 2 sides. So the borehole that's in here. Okay, then after that, we detonated that at the top, then at the 2 sides, then at the middle. So that's exactly which is follow that's in the engineer of that in the scale. Okay, so for me, let me come back into the previous one. This is that didn't show numbers, and so they actually here that's for each of that, which is have the numbers there to show when that's detonated. Okay, so then after that, yeah, so did that in the modeling. Yeah, so here this is that before of the detonation, just apply that in the in situ of the stress. So here I have very big of the in situ stress. Okay, let's look at that. So he should have a table which will show how big is that in the in situ of the stresses there. Okay, I cannot find that table. Okay, anyway, I think that's in here. That's in the vertical is about 30 megapascal. That vertical is 10 megapascal. Horizontally is that's in 30 of the megapascal. Yeah, then that's where you see that's in the stress of the concentrations there. Then after that, okay, we have that in the detonation. Initially, detonation that added the 2 sides, then you added the top. Yeah, so then you added the bottom, then you added that in the 2 corner. Okay, then after that, so we compile that in our modeling with that in the experiment of the observation. So after that, in the field, after they did that, they plotted, they caught in that in the tunnel wall to see, so what is that's in the excavations damage. So what they found is that in all of that in the crack, you can see to propagate in the upward. I think that's at that time, what when I was working as a PhD student, I investigated the problem. So they asked me, so why this cracking which propagating that since upward? Yeah, I concluded that using the RFP at that time, I think that this is caused by the higher of the horizontal of that stress. Yeah, I think that we have here can further to prove that, so that's caused by the higher of that in the horizontal of that in the stress. Yeah, and here we compared this in the monitoring of that in the wave of that distribution as well. Obviously, when I use the RFP, I wanted to be able to get this. Yeah, but I know we are of RFP have that in the dynamic of the versions as well. Yeah, hopefully can do this and that in the modeling as well. Okay, so this is that's one of the example which shows one of that's in the engineer of the problem. Okay, the other of that's in the engineer of the problem, which is is still completed by this student. So which is working building that example in China. So which is Jinping of the rock busting. Yeah, so yeah, I think that's Professor Tang. The group is working on that the Jinping of the rock busting as well. Yeah, so we consider that's a case study. Actually, is a published paper. I think that's in the this paper which is published by the Wuhan Institute. I think that after we published in this paper, so this also actually which is contacted me. He said that commented our body, so which since the field observation which is completed by him, we have that based on that in his paper. Yeah, he actually thinks that we have that in the body, which is where body in the rock busting, which he observed that in the field. Okay, so this is that in one of another of that in the case we applied in that in the engineer. Okay, another one which is a little bit that's confidential. So I won't really talk about that in details. I just show you that I completed that in a consulting project for an Australian company, which is called the Good Associate of that company. Yeah, so what they are interested that in, which is interesting that they called geothermal of the burst. Geothermal burst, which is quite similar to our cases. So the important cases, they are wanted to understand what is that in the discrete in the fractions network. So you can see here, I did a number of that in the modeling. When I have that in the, for our model, I introduced the discrete fractions network, and they see how that's the geothermal of the vapor, which is flow through this the discrete fraction network of the model. So then after that, which is presented that the called the geothermal of the burst. Yeah, so that one, yeah, since that's a consulting project, yeah, I'm not allowed to publish something. Yeah, but I get that, yes, to earn above that the okay, Australian dollars is above that the 10,000 that's the Australians of the dollars to do that in the consulting of the project. Yeah, I think that so it's right. We still have a long way to do apply that in the engineer of the problem. Yeah, so we did a number of that in the modeling together with CSO for that in the rock blasting, the field scale of the rock blasting as well. Yeah, so for that one, so we have not published the yet. Okay, so maybe I show you that in one of that example, we consider to do the preliminary of the study, we do that for the field scale of the ring of the velocity in the mining. So when we okay, so let me find it. That's yeah, I have that in a number of that in the videos here. Okay, so let me find it one of that in the video. So log velocity in the ring velocity. Ring velocity. Okay, so let's look into this one. Yes, ring velocity is that in the mining. So we dig in a number of that in the ring, and in each ring, so we have a number of the borehole. You can see here. So this is that's the fan shape of that in the borehole. Each of the borehole. So here is about that's 40 of that meters, and here have that in the because the delay is not initiated that at the beginning. Each of that in the borehole, which is detonated separately, then to cause that in the rock fracture. So what is they are interested in that how this they adjacently the borehole, which is interacted with each other to result in the fracture. And they are also interested in that. And so when we found that in the fragment there, so then here, which were clappers which were involving the gravity of the floor. And they wanted to understand that in the gravity flow as well. Yeah, obviously, so here we are still that's quite far away, yeah, from that the requirement. Yeah, but this is that yeah, demonstrating this is promising for us to do this type of the research. Yeah, so in summary, is that still we have this have very limited of that the engineer applications. Most of that which is involving the laboratory scale of that the calibration.
Okay, thank you for Professor Liu for showing these case studies. 王老师，
Very
还有没有问
excellent.
题？
I always been here. I not.
Oh, great! Thanks.
Yeah. I give up another conference, so I've always been here listening very carefully.
Oh,
But
great!
my internet speed is not, my internet speed is okay. But I listen very carefully. Okay.
Yeah, I hope for that through our this series of that in the presentation, so we will have some of the students be able to use this software. And so I remember when I was in China to working for the master's degree and that's in the PhD, actually we have a very small group. Yeah, even for Professor Tang at that time, yeah, just had 2 or 3 of the master students, or 2 and 3, and then another 2 and 3 of the PhD students. But I can see here, yeah, so we have here about that 20 of that the students here. I think that's so now you have a huge pool of that the students. Yeah, so some of the students yeah, will be interested to do that in the modeling. Yeah, hoping they can use this software help us to do the calibration and to do that in the engineer applications as well. Especially consider now in China how many of that in the engineer of that in the project. Yeah, hopefully through this collaboration, so we can apply this into the engineer of the project in China as well.
Okay. Well, I think the conference today is okay. Its time is now okay.
Okay. Thanks again for to Professor Liu for his excellent report. Thank you.